Okay, this is the section 2.6 notes we voted on in class to make this a full video so that you guys could have more time for review for the test one. The skills that we're going to focus on in 2.6 is solving linear inequalities, graphing the solutions that we get, and writing them in interval notation, learning about the reciprocal property and how to use it, and to solve some absolute value inequalities. Okay, so the big thing is, what is an inequality? Well, an inequality has either a less than, a greater than, or a less than or equal or a greater than or equal to symbol instead of an equal sign. We can solve these. You could also plug in random numbers on the number line and see if they produce true or false statements. Now, there's obviously going to be more than one solution, usually to an inequality. The solutions we get are then going to be written in interval notation. So again, you can read a lot of this in more detail. We're just going to hit the highlights and then start working some problems. And then the graph. So like if I wanted to graph, this is a graph that represents, let me put this here. This graph right here represents 2 is less than x and x is less than 5. So x is between 2 and 5. And notice that we use, some people remember at books you use open circle when you had just a less than, or if you have an equal to, you use a closed circle. Open circle in our book is the same thing as a parentheses, and closed circle is the same thing as a what we call bracket. And I did write that somewhere else down here. You'll see that in just a second. Yeah, so if you have an equal to bar, this is the same graph, except we're using brackets on the end to say that 2 and 5 are included. This is a chart that has a lot of pictures of how graphs relate to the inequality and the interval notation. Interval notation, by the way, is just a start, comma, and end, which means that your answer is all values between. So that's what we mean when we write interval notation. And this side, you either enclose it either in a parentheses or a bracket, in a parentheses or bracket, depending on equal to or not equal to. Okay, let's start off with the first little problem. We're going to be sketching some of these. So we're going to sketch x is less than or equal to 5. And it doesn't matter if you put it in the center or if you put it with 0 in the center. Sometimes it's just easier to put the number you're talking about in the center if you're making the graph yourself. Put a few numbers on each side. We are going to be doing, we're supposed to express the inequality as an interval notation and sketch the graph. Sometimes it's easier to sketch the graph first and then write interval notation. So x is less than or equal to 5 means that we use a bracket because that's like closed circle. And notice I'm opening it to the left because less than means shade to the left. Now when you write your interval notation, you obviously know it's going to end in a 5 because that's the last thing we shade. We read this from left to right. This side over here is actually what we call negative infinity. Infinities always get parentheses because you're not allowed to include a concept like infinity as an endpoint. It doesn't end. So then if we did x is greater than negative 3, so here's negative 3, negative 4, negative 2 are on both sides. Greater than means we're going to shade to the right. It doesn't have an equal to, so we're using a parentheses. Trying to make those look different than my bracket is a little hard. Shading to the right. So that would be parentheses negative 3 because that's the first thing we shaded, comma, and this is positive infinity. Right here, this is saying we're going to shade between negative 3 and there's negative 2, negative 1, 0, 1, 2, 3, 4, and 5. So a bracket on the negative 3 because this has an equal to bar, a parentheses on the 5 because it does not have an equal to bar, and x is somewhere in the middle. So as a interval notation, that would be negative 3 with a bracket up to positive 5 with a parentheses. We can do something similar for these. This is negative 3, negative 2, negative 1. This one is parentheses on both sides because you have no equal to bar. and x is still in the middle, so we shade in the middle. So that would be -3 to -1, both with a parentheses. And then the final one, this is in the wrong order, so sometimes I fix that. The way you fix that, because you want it to go least to greatest, you switch this, and you take the signs with them, and you flip them the other way. So if they were both going right, they need to both be going left if you flip it around. So if we graph that, that would be, here's -5, -4, -3, open on the -5, closed or bracket on the -3, and x is still in the middle. And it's a parentheses and then a bracket. Okay, these ask you to write this as an inequality. That means like this, like these originals that we started with. So notice this is from 0 to 4. There's no infinity. So if you're going from a number to a number, you are trapped in between. So x is definitely less than 4 because they do not have the bracket, but x is greater than or equal to. So notice this is still pointing as a left point because x is bigger because x is on the right side. And this would be 0, and it's opening up to x. So it's going to be 0 less than or equal to x less than 4. Similar thing here, this would be 3 is less than x, which is less than 7, because both of those are parentheses. There are no equal to bars. When you have an infinity, you're either going to be completely greater or completely less than a number. So this is going to positive infinity. So, and it's a parentheses on the -3. So that would be x is greater than -3. This one's going to negative infinity, so we're shading to the left, or less than, and it's got the bracket. So x is less than or equal to +2. If you want to solve an inequality, you just have to get x by itself. The only trick is there's one rule that we have to be careful about. You can pretty much solve these just like regular equations, but if you, and I'm going to highlight this here, if you multiply or divide both sides of an inequality by a negative number, it reverses the inequality's sign. So for example, -3x less than 15. Because I'm dividing by a -3, I am dividing by a negative, so I must flip this to be a greater than. That is not true if you see this guy, so just +3x is less than -15. I'm dividing by a positive here, so I keep this the same. The note is, the part over here, the one you're trying to get, when you get x by itself, if the other side stays its original sign, it should not be flipping. If the side that's not got x on it changes signs, it does need to flip. Compound inequalities are just inequalities where you put two things together. So the ones that we were just looking at, like -2 is less than x less than 2, that is a compound inequality, and it's an and statement because you can break this into x is greater than -2 and at the same time x is less than 2. In an and situation, you have to find a solution that makes both inequalities true. A union is where you say everything that belongs to either set is an answer. So in a union, you would actually have to have an equation, and then you'd have to have the word or, and you would have to solve both and see what solutions work for either the first one or the second one or both. Okay, so we won't be doing much of those. That comes kind of in with the absolute value stuff. We'll talk about that then. If we're going to solve some basic ones, so I'm going to try to get rid of all the fractions, and I can do that as long as I multiply everything by the same thing. Looks like I'm going to use 12 as my LCD. So writing it in front of each of the terms. That would make this 4 goes into 12 3 times. So that would be 3x. 12 times 7 is 84. Less than or equal to. 3 goes into 12 4 times, so that would just be 4x. And -12 times 2 would be -24. A lot of people try to avoid getting negatives in front of their x. I don't. My goal is always to get x on the left when I'm doing inequalities. Those are easier to graph. So I'd also subtract 84. And that would make that -108. But the problem is we want to divide by -1 to get rid of that negative in front of the x. So instead of a less than, this one ends up being a greater than or equal to. Now, what else do we need to do with this? Express it in an interval notation. So in interval notation, this would start out at 108 as its first number you shade, and it is a bracket because of the equal to bar, and it would go all the way to positive infinity. Okay, on something like B and C, these are called compound inequalities like we were looking at. You can solve these all in one step just by considering multiplying and adding and subtracting to all three sides, because you essentially have a left, a middle, and a right. So if I multiplied, I'm going to change colors to make this a little easier so I have some room. Multiply all three parts by 3 to clear that fraction. So that would make this -6 less than, this 3 cancels, so that would just be 4x plus 1, and 0 times 3 is just 0. We would subtract 1 from the left, the right, and the center to get x by itself in the middle. That's our goal. So that's -7 less than 4x less than or equal to -1. And then if we divide everything by 4, we get -7/4 is less than x, which is less than or equal to -1/4. And as an interval notation, sorry, I wasn't paying attention. It would be a parentheses on the left side because you have no equal to bar. And you go all the way up to the next endpoint, and it has a bracket. So this next one, I would multiply everything by 3 to clear out that denominator in the middle. So this would be 15 is greater than or equal to 6 minus 5x, which is greater than 6. I would subtract 6 from all three parts. So that is 9 is greater than or equal to -5x greater than 0. We would divide everything by -5. Now, because we're dividing by a negative, that flips all of our inequalities. So this would be -9/5 is less than or equal to x, which is less than 0. So if I wanted to write that in interval notation, -9/5 would have a bracket all the way up to 0 with a parentheses because of no equal to sign. Okay, if it was me, I would subtract the 3 first since the whole middle does not have that 4 underneath it. So this would be -5 is less than 1/4 x less than or equal to 2, and then we can multiply everything by 4 to get rid of the fraction. So this would be -20 is less than x, which is less than or equal to 8. So in interval notation, that would be parentheses -20, comma 8 bracket. Okay, for 8, we would need to FOIL this out. So this is x squared plus 3x and minus 3x cancels, so that's -9. We would also need to FOIL out x plus 5 times itself. That is x squared plus 5x plus 5x, so that's plus 10x, and then plus 25. Try to move the x squareds to be together because that's something we haven't seen yet. They would both cancel out. So you have -9 and it's greater than or equal to 10x plus 25. I would go ahead and just solve it for the way it is, so I'd get the x by itself on the right. Just this case, it didn't work out to move it all around. So that's -34 is greater than or equal to 10x. Divide both sides by 10. X is greater, or excuse me, -17/5, because I'm going to reduce that, is greater than or equal to x, but I want to write it in a way that I can read it better. So if you want to switch the sides, that's okay if you switch the inequality. So it needs to still point to x. So this would be less than, so -infinity with a parentheses up to -17/5 with a bracket because of the equal to. Okay, so I kind of went through those fast, but those are all just basic like solving equations. You just have this interval, and the multiplying or dividing by a negative can change your inequality. Now, these I want to talk about for a second. These are absolute value inequalities. And what we mean by this is I like to draw a picture and think of what they're saying. If you have x as your center, which most people would say in absolute value the center is 0, there are two ways you can go a distance away, because absolute value measures distance. You can either go to positive a, or you can go to the left, which is a negative direction. When we say our distance from x, or 0 in most cases, not always, but if you have just x inside, our distance from 0 needs to be less than a. That means you're talking about anything between negative a and x and anything between x and a. So you're going to get something where x is in the middle. So the way we set these up is we take whatever's inside here, it goes right here. So that's called the argument. And we set it between a negative of this number and a positive. Now, so like for example, if I had x is less than 3, I would say negative 3 is less than x, which is less than 3. So notice this goes in the middle, and you use positive on the right and negative on the left. There is one special case. If you have the absolute value of x is less than negative 3, absolute value is always positive. So can a positive ever be less than a negative? No. That's just like when we had absolute values equal to negatives. So this case right here is always automatically no solution. So that one is just a special case. You do not want a negative to be on the opposite side of a absolute value and a less than. Okay, the other case is when is our distance greater. So just as a picture, if x is your center, here's a, here's the opposite of a, so we went both directions. If you want your distance to be greater, you don't shade in between, you actually shade away from x. So we go to a and start shading away, go to negative a and start shading away. So that actually breaks down into two cases. You're either less than the negative direction, or you're greater than the positive direction because you're heading in opposite ways. So for example, absolute value of x is greater than 3. We would say either x is less than the negative option, that heads you towards negative infinity, or x is greater than the positive of that number. Again, there is a special case. If you say my absolute value is greater than a negative, absolute value again is always positive. A positive is always greater than a negative. So this would actually be all real numbers. So it would be the entire number line, negative infinity to infinity. So only if it's a greater than and a negative on the other side do you do that case. These are reciprocal properties. I believe this one got typed twice though. This should say less than and less than, so just change those. This says if a is positive and there's a positive number on top of a fraction, then the a in the bottom would still keep this whole fraction positive. If a is negative and you have a positive over a, then a is still going to make the whole fraction negative. So that's just a rule that says you can use signs to help you determine how to solve some things. And I'm going to use that in the next examples. Okay, so notice that 3 is positive. So the top of my fraction is positive. I want my fraction to be less than 0. Less than 0 means that the fraction needs to have an overall negative sign. Well, if your top is positive, the only way for that to happen is the bottom must be negative. And that makes sense. That's kind of like that reciprocal property. If this is positive and this is a less than, the bottom has to be negative. So all we need to figure out is when is 2x plus 5, and this is a key here. You don't do equal to 0 when you're talking about a denominator. We do not want our denominator to equal 0. So if we were to solve this, we would subtract the 5 over and divide by 2. And they want us to write this in intervals. So for this first one, it's negative infinity to negative 5 halves. This is be careful with something like this. That negative, if it was me, I would write it on the top. Or I can make my life easier. I could distribute it to the bottom. A negative can be distributed to either place. So if we distribute it to the bottom, that would change both of the signs in the bottom. Notice that the top is positive again, and we want to be less than 0 again. So that means that your bottom must be negative because you want this to be opposite signs. So we'd let negative 2 plus x be less than 0 and add x over, and so we find out that x has to be less than 2. So from negative infinity to 2. This is a funny case. 4 is positive, always. X squared is also always positive. So if you add 4 to that, this whole bottom is positive. A positive over a positive cannot be less than 0, because that would mean it would be negative. So this is going to be no solution or no real numbers, whichever way you want to write that. Okay, now we have a couple of the absolute value examples. This one is a less than, and this is positive, which means it's not one of the special cases. So when it's a less than, you put the x or the argument in the middle, and you do less than or equal to on both sides, and we say it's either -7 to 7. So that would be -7 to 7 in brackets. If you have a greater than case, and this is positive over here, then you either have the inside is less than -2, remember that helps us go towards negative infinity, or the inside is greater than +2. So that's the or case. That x is supposed to have a negative on it. So we divide by -1. That makes this flip to positive. So this is one solution. Or we divide by negative here. That's going to flip this to a less than and change that sign. Now, how do we write something like this? Well, if you think here's -2, here's 2, you have a parentheses, you're shading to the left of -2. You have a parentheses, you're shading right. If you wanted to write that in interval notation, it's negative infinity to -2, and this one is 2 to infinity. When we have a jump, we use this symbol called a union to tie them together. A couple more real quick. If we wanted to solve this one, you have to isolate that absolute value first, just like when we did equations. So I would add that over. That would make this 0.4. And then this is a greater than. So because of the greater than, you're going to do the or case. So set the insides either less than the negative case or greater than the positive case. So in this case, I would add 3 over, and I would get x is less than 2.6. In this case, I would add 3 over and get x is greater than 3.4. So again, one's going to negative infinity, the other one's going to positive infinity. So negative infinity bumps up to 2.6, unioned with 3.4, which then goes to positive infinity. If you need to graph it to see that, please feel free. On the next one, again, isolate your absolute value first. So I would add 2 over. In fact, I want to make this one a less than, just so it'll look a little different. So this is 2, that's -11 minus 7x in the absolute value. That's less than 12. Divide by 2 on both sides. Keep your absolute value intact. That would make that 6. And because it's a less than, because I wanted to do one that was a less than, you put the -11 minus 7x in the middle of 2 less than symbols, where one side is -6 and the bigger side is +6. So I would add 11 to all 3 sides. That makes this 5 is less than -7x, which is less than 17. Divide all 3 sides by -7. That would make this -5/7 is greater than x, which is greater than -17 over 7. You don't have to rewrite this if you just realize that greater thans need to be written backwards. So this would be -17 over 7, comma -5 over 7, because you're shading in between those two, and you always list it from least number to greatest number. And then this one is just here to throw you off to see if you're paying attention. You cannot be less than or equal to a negative. Remember, this is always positive. No matter what we plug in here, absolute value is a positive. A positive cannot be less than a negative, so this one would be no real number or no real solution, however you want to write that. And that's it. So that is all of the notes from 2.6.